Now we're starting with number 9. This is problem number 9. We already finished 7 and 8, and we're going with number 9. And number 9 says, given the iron metal reacts with bromine, so iron metal solid reacts with bromine. It doesn't say what state of matter, so you don't have to, but it's gas, bromine gas, to produce iron bromide, which is going to be solid. So now let's balance the equation. And it's going to be 3 bromine. So I have to put a 3 here and a 2 here. 2 by 3, 6, 6, and 2 irons. This is the balance equation. What mass of bromine, right, 2, will be required to react completely with 210 grams of iron. Again, let's do our molar mass. So for iron, I'm going to put the whole 55 according to periodic table you're going to use on the exam. 55.845 grams per moles. Okay. Now bromine is gonna be 79.904, but we have to multiply by 2 because it's the atomic. So it's gonna be 159 is 79.904. We multiply by 2 and it gives you 159.808 grams per moles. And then let's go ahead and calculate the iron 3 bromide, which is gonna give you iron 55 plus 3 times 79.904. It's gonna give you 295.557 grams per moles. And I'm telling you, to remember just to write down, if you multiply 79, you made a simple mistake. I wrote it like that to not waste time. But if you make a simple mistake on this, it's going to count all wrong, and I'm not going to be able to see where was your mistake and give you partial points. So you got here, and it says what mass of bromine would be required to react completely with that. So what are they asking this? So what do you need to have to calculate this? You have the grams of iron, but you don't have the moles. So again, from grams of iron, we go to divided by the molar mass of iron. We go to moles of iron. Then we do the stoichiometry ratio, the equation, right? And it's going to be 2 to 3. 2 to 3. So we're going to get the moles of Br2 of bromine, because that's what they're asking for. And then we convert it to grams, because that's what they're asking for. We convert it to grams by the molar mass of Br2. So you see, we're using 2 molar mass here, and later on the problem we're going to use more molar mass. So it gives you the grams of Br2. That's what we're looking for. So 210, let's start first. 210.0 gram divided by 55.845. So the number of moles of iron are gonna give me 210 grams, right? Divided by 55.8 and 45, but I'm gonna show you 845 grams per moles. And that is gonna give me 3.76 3.76041 moles of Fe. And still we need to do calculations, so I'm not going to round it yet. So here would be 376,041 moles. So again, we do our little 2, gives me 3, 376, give me x. So 2 over 376, 3 over x. 2 moles of iron. Then we put the bottom, the calculation, the 3.76, we put the ones we have on bottom, moles of Fe equals 3 moles of bromine, that's the coefficients of bromine, divided by x. Why? Because that's what we're trying to find out. So x would be, and I'm going to do it real quick, x would be 3, it's going to be, again we cancel out moles of iron and moles of iron, and it's going to be 3 by 3.7601 moles, right? This divided by 2. So x is going to give you 5.6406 moles of what? What we were trying to do to find out the moles of bromine, right? By the way, I forgot to put Br2 here. So moles of Br2. Now we need to find out the mass. How do we find out the mass? If you're a little bit confused with that, go back to a flow chart, what I was saying. We multiply by the molar mass of the Br2, which is 159.808. I'm trying to get space here. Hold on. Okay. So it gave us the moles, the grams of Br2 are going to be equal to, the moles was 5.6406. 5.6406 moles of bromine multiplied by the molar mass, which is 295 of bromine. That it's twice the 79, which gave us 159.808 grams per moles. Cancels out, and it's gonna be 901.415 grams, and 3 sig figs again. All of them are 3 sig figs. Just check it out. 210 point. That's the data they gave us. 210 point. You see? Gonna give us 901 grams. That's the mass of Br2. Of Br2. Well, let's keep on going. What is the mass of of iron 3 oxide? Could be theoretical produce. Theoretical means it's with your calculations. So again, using the mass of 210, do you remember we already calculate the moles for this? Well, let me put it on pause, and I'm gonna go ahead and copy the equation and the data. Okay, so we save time, video time. So with 210, we got 376,051 moles if from part A. So if you remember here, we already made the calculation divided by the molar mass. Now they're asking for the theoretical yield. Theoretical yield of FeBr3 is the only product. So what are they asking? To calculate the amount that you're supposed to obtain. After the experiment, you see you get the actual yield. But this is, before you start, you want to see how much do you think you're going to get. So you got here again 2 moles of FeS. Again, look at, make your own flow chart like I was telling you, because we have to get to grams again. So 2 moles divided by 376,041 moles of iron. On top, 2 moles of iron 3 bromide. Doesn't matter the state. And it's gonna give me, for the calculation, it's gonna give me 2 multiplied by 3.76441 moles of Fe divided by, yeah, by 2. Yeah, this and this cancels out, so it's gonna be the same. And moles of Fe and moles of Fe, so it's gonna be the same. The moles of iron are gonna be 3.76041. Oops, of iron bromide. The moles of iron bromide, let me get it a little bit lower. The moles of iron bromide are gonna be equal to, oh, Dios mío. I waste so much time, but I want to go faster and I can't. Br3. So the moles of iron bromide would be equal to 3.76051 moles. Then this you multiply by the molar mass. So the grams of FeBr3, remember the flow chart, is 3.76041 moles multiplied by the molar mass of iron 3 bromide, which is 295.557. 295.557 grams per moles, and grams per moles cancels out. And remember, this is in 3 sig figs again. So this is gonna give you the grams of iron is gonna give you 901. No, that was the other one. Yeah, that's it. No, that was the other one. So we are, okay, here it is. It's gonna give you one, it's gonna give you 1,111.41499 grams taken to how many sig figs? Do you see it? We got 3 again because it's 210 point. So it's gonna be 1, 2, 3. So what you need to do? you need to put it like that with a zero. That would be 3 sig figs. Or you need to put a decimal point in, this is a comma, in scientific notation with 3 sig figs by 10, and it's 123 to the third grams. Any of that is completely valid. Okay, usually in scientific notation is the best way to do it. Now only 674, what is this? The actual. You have to learn how to read the problem. That's one of the most difficult things. The actual yield. Six, sometimes when I'm in class and I have to read a problem that I solved it time ago and I don't know how to solve it if I'm not paying attention, right? Now, recover from the reaction. So really, you did the experiment and you got 674. What were you supposed to get? What was your theoretical yield? 1.1 by 10 to the third. Okay, 1.111 by 10 to the third, or 100, like I said, grams. You multiply by 100, and that is gonna give you 60.72%, which is gonna be 3 sig figs, 60.7% of yield. Okay, so go to problem number 10. I think so, yeah. Problem number 10. Powdered aluminum and iron 3 oxide, okay, react with a large evolution here according to the following equation. Okay? In one experiment, 0.360 moles of aluminum was added to zero point 0.2 moles of iron. How do you recognize the limiting reagent? They're asking, but immediately when they're giving you two reactants, you know, if they telling you in excess or they giving you only one reactant, you know you don't have to calculate it. But when they're giving you two, they don't say which one is in excess. You have to calculate. You have to find out which is the limiting reagent. So doing that, the first thing is aluminum is equal to 26 point. Let's give you the molar masses. I'm looking at it and I don't know if I calculate the molar masses. Well, we don't need to yet because it's given in moles. So when we have to find out the grams, it's given in moles. So let's simplify ourselves. Okay, so if we got here 0.360, what do we need to do to find out the limiting reagent? We want to pick one and find out how much of the other one you need. Okay, so you have to ignore first that you got this. If I pick aluminum to find out how much iron oxide, iron 3 oxide I need to get, then I compare it to what I have. Okay, this is what I have. Okay, of iron 3 oxide. So this would be our starting point. So let's do it. If you got 360 moles of aluminum, do it this way. Okay, how many iron oxide are you going to need? 2 divided by zero point 0.2 moles of Al divided by 360 moles of Al equals 1 mole of Fe2O3 divided by X. So moles of aluminum and moles of aluminum cancel out, and you would have 0.360 moles of iron, by the way, moles of iron oxide, divided by 2. Okay? I cross multiply, and that gives you the amount you need of iron oxide that will react completely with 0.360. So it gives me point 0.180 moles. Now this is what you need to react with all the aluminum you have. When I mean pick one, is that I'm saying, no, let's pick that we have this one. Let's suppose we have this one and we want to calculate what we need, okay, to react completely with this one. If it reacts all of it, if we have enough, then this one would be the limiting reagent because that means that this is in excess. If it's equal to zero point 0.2, for example, what we have is gonna be okay. But let me keep on going and do it step by step so I can explain myself. 0.80 moles you need of iron 3 oxide. Now you go ahead, right, and compare it. This you compare it to the amount you have given. Now, which is higher? Or you subtract, and if it gives you positive, right, the amount given minus the amount you need, if it gives you a positive number, it's because it's in excess. In other words, you have zero point 0.2, right? And you need only 0.18. So you need less than what you have. So 0.200 moles minus 0.180. You don't need to do that if they're not asking for the excess, but you already know it's going to give you 0.02 moles, and it gives you positive, so that means that this is the excess. So if iron oxide is in excess, which would be the limiting reagent? Aluminum limiting reactant. Okay, let's go to the next question. Calculate the theoretical, no, yeah. Calculate the theoretical yields in moles of iron. What does it mean, the theoretical yield? Remember, and it says iron. So theoretical yield will be the amount of iron I'm going to produce. But it's not in the lab. Not after you did the experiment. How I said that, I like that. It's before. It's what you're supposed to get. And don't forget it. I'm going to put it in big letters here. Okay, and red. You use limiting reactant for your calculation. For your calculation. Okay, let me copy and paste. Okay, I copy and paste the equation again. Now, what are you going to use? They're asking for the theoretical yield of iron. Be careful, because if they ask you for aluminum oxide, will be this one. So what are they asking? How much are you supposed to get of iron? So they're asking you to calculate this. But from where? Having 3.360 moles of aluminum reacted, because as this is the limiting reagent, you know if you take this one, it's going to be risky because then you have to take the one that reacted. So forget about it. Just get the limiting reagent as your base for every calculations. So you're going to get 0.360 moles, right? Now again, our 2 moles of aluminum, 0.360 moles of aluminum, and they cancel out, equals 2 moles of iron. And by the way, they asking you for moles. You don't need even to convert it. X. So X is equal 2 and 2 cancels out. So you're going to have the same. 0.360 moles of iron. Mhm. And I think that's for number 10. Number 11, okay? Number 11 says, let me see how much do I have. Okay, I would keep on going. And checking the other one was, I will keep on going. And the following 11, before stopping this, the following reaction occurs when aluminum is heated with oxygen. Balance the equation. I copy it just in case I need to take it down again. Do you see how important it is to have the balance equation? Because, how I said again, recipe. So 44366. A reactive mixture contains, again, we're going to have the same 50.0 grams of aluminum and 50.0 grams of oxygen. So why don't we do something? Why don't we calculate the molar mass over here in some place? And again, calculate it and I'm going to give it to you. Okay? And aluminum would be 26.98154. You know how to calculate the molar mass. I'm not going to calculate it because it's going to take too much time forever. O2 would be 31.9988 grams per moles. And then aluminum oxide, and it's going to be 101.96128. So it's going to be, okay, what do we need to do first? Again, they're giving us the grams and grams. We need to convert it to moles both. So we can have this in moles and compare it, okay? So let's calculate the moles of aluminum first. The one on the left. Okay, moles of aluminum. And it's going to be 50.0 grams divided by 26.98154 grams per mole. At least I'm writing faster with the pen. Equals how much? And it's going to be 1.85312. 1.81, 1.8531 312 moles of Al we have. Again, how I said. Okay, we're gonna check what we have for both. Now for iron. Iron would be again, for oxygen, moles of oxygen of O2 would be equal 50.0 grams divided by 31.9988 grams per mole. And it gives you 1.5625559. This is the O2 we have. Okay, keep it there because now, which one do you want to choose as our reference, our starting point? What would be our starting point? I decide that with aluminum, right, I'm gonna see how much oxygen I need. Okay, so just keep this And we're going to use with the stoichiometry ratio, I'm going to use here 1.85312 moles. And I'm going to find out, this would be our next, how many oxygens do I need? So again, 4 moles of aluminum, of Al, is divided by 1.85312 moles of aluminum. It's gonna be 3 moles of O2. Let's find out how many is gonna react with the amount of aluminum we have. So it's gonna be 3 by 1.85 divided by 4. Divided by 4 is gonna be equal to 1.13894. So you don't get lost. What are you finding here? You're looking for the moles of oxygen that will react with the amount of aluminum you have. You are looking for the moles of oxygen you need. Okay? You need moles of O2. You need uh, you need to react with aluminum amount of aluminum with the moles of Al given. Do you see? Because that's the only way of doing it. So let's look what we need and let's compare it to what we have. Okay? Which one is higher? What we have. So that means that we have more than what we need. That means that the oxygen is in excess. Okay? Oxygen would be excess, and the limiting reagent would be again aluminum is the limiting reactant. Let's go with letter B. And letter B says, if I find it, how many grams of aluminum oxide will form? First of all, I'm going to take this to, I'm going to again pause so we don't waste time. Okay, the question, the letter B, I have everything ready. How many grams of aluminum oxide will form? That's what we need to find out. That's the theoretical yield. Okay, this would be theoretical yield. Okay, so we got this, right? How much are we gonna get? And that's what they're asking for. What do we need to take to calculate that? The moles of aluminum, which is the limiting reagent. How many moles of aluminum do we have? Up here, 1.85312. So it would be 1.85312. We have it already calculated. That's why I say put it in a box. 1.85312. 312 moles. So we got here 4 moles of aluminum divided by 1.85312 moles of aluminum, right? And we're going to calculate how much aluminum oxide did we form. 2 divided by x. But again, remember the flow chart again. We're going from moles to moles of aluminum oxide, and then we have to multiply by the molar mass. That's why some students like to do it all in a row. So we're going from moles of aluminum to moles of aluminum oxide, and then we're going, and this is by the ratio 4 to 2. And then we're going to the grams by multiplying by the molar mass of aluminum oxide. You need to do those kind of things so you don't get lost in the problem. And it's going to be the grams of aluminum oxide. So let's finish this, the x here. And x would be, and this is moles of aluminum oxide. So the x would be equal to 2 by 1.85312 moles moles of aluminum, not moles of aluminum oxide divided, sorry, by, 2 by 183 divided by 4. So the moles of aluminum oxide, let me write it down here, that x is going to be equal, if you do it, it's, where is it? Is there a missing a question? How much O2 needed to consume all? No, no. Um, okay, I put it differently. Okay, so you got that it's gonna be 0.92656 moles of aluminum. So now what do you have to do? Multiply by the molar mass. You see? Multiply by the molar mass here to get the grams. So grams of aluminum, and this, by the way, aluminum oxide. This is what we were doing. Aluminum oxide is gonna be 0.92656 moles. So now, as you did, like I told you to do, right? To get those smaller masses at the beginning, we have it already. 101.9628 grams per moles. So cancels out, and look, the grams of aluminum oxide is gonna give us 94.47324 grams, or 36 then. But you take it to how many sig figs, by the way? Let's look at our problem initially, and it's 3 and 3 sig figs for the grams given data, so would be 0.5 grams. Okay, and that is grams of aluminum oxide. Don't forget to put me the title of what you're giving me. Okay, now how many grams of excess reagent will remain? That's why I like to put that question before, because now we have to go back. But we did calculate it, because when we found that the excess was the oxygen, right? And you have 156, right, moles of oxygen. And what did you need it to react with all the aluminum? 138. So we need to subtract the 156, oops, 156.562559 minus 138,984. So for letter C would be 1,5. But they're asking for, and I did it two ways, so yeah, I can prove it. They're asking how many grams in excess. You have two choices, or subtract the moles, right? And then the difference you multiply by the molar mass of oxygen because oxygen is the one in excess, right? And how? Well, okay, we get 156. Remember, this was the amount we got 156 2559 minus moles minus 1.38984 moles, and that gives me an amount in excess of 0.121719 moles of O2 excess. Now, what do? We multiply by the molar mass of O2, remember. Moles of O2 multiply by 15.9994 grams per moles. And it's gonna be 55268, 5.5268 moles in excess of O2. And taken to 3 sig pigs again, it would be equal to 5.53 moles. Grams. We're finding out the grams. Whoops. Yeah, it's the grams. So this would be grams of O2 in excess. Grams of O2 in excess. Now, if you look at this, right, you can also do it this way. You can find out the amount needed and you converted it. This is what you need. You converted it to mole, to grams. And then you subtract to the 50 that you initially had. So you subtract grams to gram. It's the same thing. I rather do it moles to moles because you already had to calculate the moles of oxygen. Now before I get to number 11, I think that's what we have. No, number 12. Number 12. I'm going to stop it here, post this video, and then keep on going.